All right, starting off today, we're going to be looking at practicing some more of our naming. So it says here first to determine the type of compound. That's what we need to do here first before we begin. And then determine and write the, actually it should say before writing the name. I must have got that backwards. So before writing the name, not the formula, the name. Okay. So looking at number 1, what type of a compound is this? Good. The H in front's a big indicator that this is an acid. Very good. Acid. Now, I have to ask myself one question. Does it have oxygen or does it not have oxygen? HCN, do not see any oxygen. Good. So, what is the system of naming when there isn't any oxygen present? What do we need to have? Hydro. Good. So this is going to be hydro. Now we're going to put the root of the name here and Cn minus. What is Cn minus on your polyatomic chart? It happens to be a polyatomic ion. Anybody know the name of that? Cyanide, yes. This is cyanide. Very good. So we're going to take the beginning part here and put cyanic. Change the ic, hydroic, hydrocyanic acid. That would be the name of this one. Very good. Exactly right. Let's go blue. All right, now looking at this compound, number 2. What type of compound are we dealing with here? Is it acid, ionic, covalent? Yes, definitely, you are correct. This is covalent. Correct. Now, since it's covalent, what do I need to include in my names? What's the system to use? Prefixes. Good. Now, the only time we wouldn't use a prefix is if the first one was a 1, but this isn't a 1, this is a 2. So what is the prefix for 2? Di. So this is going to be di, and then you just write the element name, chlorine. Dichlorine. And then what's the prefix for 7? It is hept. So, and remember this is oxide, so we're going to drop the A off. So this is hept oxide. No double A or AO or OO. Sorry, no double O or AO. So we drop off the first one. So this is dichlorine heptoxide. Alrighty, moving on to number 3. What type of compound are we dealing with here? What does that Ag automatically tell me? What do we got? It's ionic. Very good. This one's ionic because Ag happens to be a what? What type of element is Ag? It's a metal. Good. And when it has a metal or ammonium in the front, obviously it's going to be ionic. Now I can also see there's a polyatomic in here, which gives me a huge indication we're talking about something that is ionic as well. So what is Ag? How do I name that? Name the metal. What's the metal name? Silver. The next question I ask myself is, silver a mom, does it need a Roman numeral? Is it a multiple oxidation? No, it is not. Remember, it is one of the few that is an exception. It does reside in the transition metal section, however, it does only have one oxidation state. Silver is +1. What are the other two that are also exceptions here? That we have to know their oxidation states because they only have one. And they're in the transition metal section. There's two others. Zinc, good. And cadmium. What is the charge for zinc and cadmium? +2, good. So these are always +2s. These ones we have to know, never get Roman numerals. Good. Now, I look on my polyatomic ion chart. What's HPO4? HPO4, name it, let's go. Polyatomic ion has 1, 2, 3 elements in it. Yes, it is hydrogen phosphate. Not to get it confused with dihydrogen phosphate. Dihydrogen phosphate would H2PO4, and this would be a -1, just a minus, whereas HPO4 is a -2 for its charge. And what you'll notice, I don't know if you noticed this, but PO4 is -3. So this is phosphate. You add a hydrogen, the charge goes down by 1. Add another hydrogen, the charge goes down by another 1. So that's kind of a nice little pattern. When you add a hydrogen, it takes away 1 from the charge. Another thing to look at. So this is hydrogen phosphate. Very good. Another little pattern to see. Okay, number 4. What kind of compound we got for number 4? Acid, good. H in front. This is definitely an acid. Now, I look at my back end here because we see an oxygen. Is this an 8 or an 8? What is ClO2? Is it 8 or 8? Chlorate or chlorite? That's basically what we got going on here. Two choices. Looking at our list, ClO2 minus, what's that? It is chlorite. Very good. Thank you. And the ite changes to what? OUS. Very good. So this becomes chlorous acid. That would be the name there. Very good. Last but not least, number 5. Is that ionic or covalent? Or acid? I guess I should name them all. Ionic, covalent, or acid? What type of element is this? What's SN? The lower right of the periodic table. Good, that is tin. SN is tin. And tin, of course, is a type of what? Metal. So that means this is going to be ionic. Very good. Okay, yes, definitely ionic. Now this is tin. So the next thing I ask myself always is, does it need a Roman numeral? Is that a yes or a no? It is. It is a yes. Now, remember, tin and lead, both of these are exceptions in the fact that they do not reside in the transition metal section. They are located in group 14. But both of them have the ability to go to +2 or plus 4. So they have two oxidation states, means multiple oxidation states. Now we have to figure out what is the charge on our tin here. Well, let's look up this one. This is obviously a polyatomic. What's Cr2O7? Look that one up on your polyatomic chart. What's the name of that? It is dichromate. Good. I'm going to put the name here. Now, I know it's dichromate. What is the charge on the dichromate? So I can figure out my tin charge. What does it say the charge is for Cr2O7? It says it's -2. Good. Now there's two of them, right? So -2 times 2 is -4. So what does this need to be to add to -4 to make sure that the whole charge adds up to 0? So what should this charge be for the tin? It should be 4 plus, exactly right, or plus 4. So that means my Roman numeral here is a 4, because the charge on the tin happens to be 4 here. So that's good. You know, if you found that to be very challenging, you need to definitely do more practice and maybe go back over, you know, some of the POGL and stuff. These are some of the more challenging ones. I tried to specifically, obviously, hone in on some of our exceptions here, like the tin and lead and the silver, zinc, cadmium ideas, but also looking at some of our other polyatomics like cyanide, hydrogen phosphate. Definitely have that list accessible, ready to go, that you can pick out and find these polyatomics very quickly. Now we're going to look at, oh, darn it. That's the wrong one, isn't it? That's not on your notes, correct? Should have been NO2. Was NO2 on your notes? Well, if it was, then it should have been nitrous acid. I don't remember which one I put now on your notes, because obviously this one's saying nitrous here, but I'll fix that and repost it. Let's look at mole conversions. Mole conversions, now we're going to start looking at math again and being able to do those dimensional analysis T-charts. Definitely get out your calculator. Going to need that. If you have a hard copy of a periodic table or a periodic table to access, that's also very helpful. Going back over the mole, it's a counting unit. So let's talk about the mole again, and what do we know equals the mole? What can we say? What do we know about how many particles there are in 1 mole of any substance? Does anybody remember that number? Mole of any substance equals how many particles? And does anybody remember the name of that number? We call it something. Yeah, the 6.02 times 10 to the 23rd. That happens to be Avogadro's number. And that represents representative particles. We generally we use representative particles, but there are specific particles depending on what type of substance you're looking at. So here, Avogadro's number, if we're talking about atoms, those are elements directly from the periodic table. Ions, of course, are the things that have charges, you know, that are individual particles with charges, like sodium or sulfate or other things like that. Those would be considered ions, anything with a charge. It could be polyatomic, it could be monatomic. Now, the concept of the formula unit and versus molecules, and what are we going to identify those with? Well, we use molecules when we're talking about covalent. And covalent means sharing of electrons. That is the defining difference between covalent and ionic. Ionic does something different with its electrons. It transfers them and it forms ions. So anything covalent you would label as a molecule. And this is how I do molecules to abbreviate it, because that's a long word to write every time. So for molecules, I use MLCS. You can abbreviate it MLCS, and that way you don't have to write out molecules every single time. Now, formula units actually are for ionic. This is when we transfer electrons, become ions, and then the two ions attract together, forming the formula unit. Now, formula unit is the lowest ratio of the ions that make up the compound. Now, of course, when we get into properties and the way that the ionic compound looks, we're going to be looking at the repeating pattern of the formula unit is what constructs the lattice crystal of the ionic compounds. But we'll look at that next week. Okay, more in there. So we also, this is a lot to write when we're putting it into T-chart. So the abbreviation, you can do F dot U dot, and I know that that doesn't look very good, but it's better than writing out the entire word every single time. So you're welcome to use these as ways of abbreviating in your dimensional analysis chart for these particular things. Now, one other thing that equals a mole. We know Avogadro's number equals a mole, but we talked about something last week that also equals 1 mole. Does anybody remember what that is? It's a certain amount in 1 mole. We were calculating it. We were using the periodic table to find them. What was the term of that particular? Yes, molar mass, exactly right. Molar mass is grams. This is the term we use, molar mass. It's measured in grams, so that is going to be the measurement there. Certain amount of grams per mole of any substance. And of course, you would need to use your periodic table to find those values. Now, these are 2 of the 3 different conversion factors you can use to convert between moles. The third one's called molar volume, and we're going to look at it in a minute. But before we do that, I have this cute little parody video to show you called The Molar Eclipse of the Heart. And I'm going to have you guys watch this real quick. It's only a couple of minutes long. It's a parody off of the Total Eclipse of the Heart song from the 80s. It does have some good analogies in there, so pay attention to them because they're kind of clever, and also a little bit more information to review and help you get back to the idea of the mole and what it means. Yes, some of the analogies and whatever are silly, but the parody's really good when we're talking about the counting unit of the mole. But one thing I want to point out that they do talk about in the video is where did Avogadro's number get calculated from? It is based off of carbon-12, that isotope, because 12 grams of carbon equals 1 mole of carbon, and they factored through all of their way of calculating that is equivalent to 6.02 times 10 to the 23rd atoms. So that's kind of where Avogadro's number is based off of. It used to be based off of oxygen, but then they recalculated it, of course, and that number is constructed off of carbon-12. So I just wanted to point that out to you. That's a little fun fact that a lot of people don't really know or pay attention to. All right, so now let's look at the third type of conversion factor, and this is called the mole map. The mole map here, 3 here, mass, this was molar mass, use the periodic table, okay? Over here, representative particles, this is your, formula units, atoms, ions, molecules, all of them are types of particles. And of course, here's Avogadro's number. It shows you where to put the fraction if you're going which direction. If you're going from the mole to the particle, the 6.02 is on the top, the moles on the bottom. If you're going from the particles to the moles, obviously the particles would go on the bottom and the moles would go on the top of the fraction. Same thing here, mass to moles. 1 mole over the molar mass, and you have to calculate that off the periodic table. Or if you're going from moles to mass, you would do molar mass divided by the 1 mole. The third thing is called volume of a gas, or molar volume. And that number happens to be 22.4 liters equals 1 mole, okay, because all of this equals 1 mole. Here's another version. It shows you like which way you divide or you multiply. Okay, another type of chart showing you the mole map right here. So what is molar volume? It's based off of Avogadro's hypothesis. Avogadro did a lot of experiments and calculations. There is one of the gas laws called Avogadro's law. It has to do with the moles versus the volume, the space that the gas takes up. Now, molar volume calculated from there. One stipulation though, it has to be at standard temperature pressure. So STP is the abbreviation of standard temperature pressure. Standard temperature is 0 degrees Celsius, which should be a familiar number to you. And its standard pressure is 1 atmosphere. An atmosphere is abbreviated with ATM. Now, what is the significance of 0 degrees Celsius? What do you always think of when you hear that value? What is that based off of? What do you know about something that has any kind of 0 degrees Celsius value? It is the freezing point of water. So this is when water freezes. So that's the basis for where standard temperature is off of. Does anybody know where 1 atmosphere, or 1 ATM, what is that value referring to in terms of atmospheric pressure? You know, the atmosphere, you know, obviously has layers and layers of different gases in it. So even though it doesn't feel that different to us, that's actually putting pressure on us. But where is the 1 ATM measurement? Where is that based off of? Does anybody know? It's okay if you don't, because you probably, yes, oh, good. Very good. Glad to see somebody knows. This is the atmospheric pressure at sea level. Yes, exactly right. So at sea level, right up to the ocean there, that's how much pressure the atmosphere, you know, is waiting on you. Now, if you're in like the mountains in Colorado or something, the atmospheric pressure up there is lighter because obviously you're higher up. So 1 atmosphere is based off of how much the atmospheric pressure is at sea level. So at STP, 1 mole of representative particles of any gas occupies a volume of 22.4 liters. So this number, important number, have to memorize it, 22.4 liters. That's always 1 mole when you're at standard temperature pressure. So therefore, we say it's molar volume. Molar volume is equivalent to 22.4 liters, which equals 1 mole, which also equals the molar mass of the substance, which also would equal 6.02 times 10 to the 23rd particles of that substance. So that's where molar volume, you know, originates from. So that's, again, going back over all of these things equal 1 mole in the center. So we're going to be able to start over here with mass, and we could figure out the volume. We just have to go 1 conversion into the mole. We could start at the volume and figure out the particles. We would have to make a pit stop here at the mole and then convert further. So a lot of these conversions are going to take more than 1 step, more than 1 fraction in order to convert. That's what we're going to start out with some where they're going to be 1 step, then they're going to take 2-step conversions, and then we'll get into some that have 3 steps for their conversions. Starting here with a very good basic one, we have 10 moles of chromium, and we want to know what mass that would be equivalent to. What is the mass of 10 moles of chromium? So what you'll have to do here is we have to set up our T-chart. Okay, we're going to do conversion, so we have to show it in dimensional analysis. We're going to multiply the fractions, of course. We're going to label everything to get our correct answer at the end. But when we had a regular dimensional analysis conversion problem back from Unit 2, what always goes in the upper left corner? What do we always start with when we're setting up our conversion? The given information, which happens to be 10 moles of chromium. So that's what I'm going to write here, 10 moles of chromium. Unit substance goes there too. Now, specifically what I need to do is take my moles of chromium here, this part, and that needs to go down here. I need to diagonal that down. And it wants mass, and of course mass is measured in grams, so the grams is going to go up here, grams of chromium. So we're taking, oops, I didn't really want to do that. Moles to grams. So this is going to take one step. Moles to grams, one conversion factor. But everything equals 1 mole on the mole map. That's good. I need the periodic table though to figure out the molar mass of chromium. Chromium's right here, and we want to round everything to 2 decimal places so we get the same values here. And that would make chromium 52.00 grams per mole. Then I could take my molar mass and input it here, 52.00 grams per 1 mole of the chromium. And what you should see here then is that the moles of the chromium cancel, and we're left with the grams of chromium. Now you multiply 10 times 52. You don't even really need a calculator for that. That's going to be 520. Last thing we have to consider is significant figures. How many significant figures were in my original value over here, my original measurement? Gotta recall those sig fig rules. How many sig figs in this value, this measurement, 10.0? 3, yes, when you have a decimal point, you always start from the left and start counting. The first non-zero, everything after it counts. So this one has 3, so I've got to make this have 3. There's one of 2 ways where you can do that. You can just put a dot here. That makes that 0 significant now because you would start from the left and count this way. Some people don't like the way that looks. I understand. It's very strange. So you can write it in scientific notation too. We could go 1, 2. You could do 5.20 times 10 to the second. Now don't forget grams of chromium. You need your unit substance. You could write it this way, or you could write it this way, and you would still get, all the credit. First, easy 1-step molar, we're doing moles to mass. Moles to mass take 1 step. Now let's look at this one. How many moles are in 15.9 liters of NO2, which is nitrogen dioxide? Let's take a look here. 15.9 NO2. So 15.9 liters NO2. Start setting up my T-chart. Now, in this case, what do I diagonal down? What goes on the bottom? The liters, yep, NO2. So you take this part and you diagonal it down. Good. And of course, I'm going to moles. So this is liters to moles. So this also is going to take 1 step. Liters to moles. So we put the 1 mole NO2 up here. Now go back to my mole map. How many liters are there in 1 mole at standard temperature pressure? $22.4, exactly right. Know that number right there. 22.4 liters, exactly right. So now we can cancel that, Cancel the 22.4 liters. All right, and do the division here. 15, this one definitely want to use your calculator for 15.9 divided by 22.4. And this gives me 0.709821. Okay, so now it's time to consider significant figures. How many over here in my original measured value to start with? Correct. That should be 3. Exactly right. So we're going to keep 3. Now remember, we're going to start with the 7. This first one in front doesn't count. 2, 3. Do I round up the 9 or do I leave it a 9? Up. So this rounds it up, but that also rounds this one up. So it's a double round. So this ends up being 0.710. Don't forget moles of NO2 to complete your answer. And this would be the final answer. Like so. So far, the first 2 problems have been examples of just one-step conversions using the mole map. Now, you also should notice too in 1 and 2, the word mole is part of the problem. Let's look at one that doesn't have mole as part of the problem. At STP, how many molecules are in 64.25 liters of carbon dioxide? Now remember here, molecules, I'm going to label it MLCS because I don't want to write out that entire word. 64.25 liters CO2, okay? This is the deal though, is we're starting with liters, but can we go directly to molecules? Where do we need to stop first? Where do we need to convert it to first? Has to go to mole first. Then from the mole, we can go to molecules. So this step is the first one. This one would be the second step. So this is a 2-stepper. I know that it's going to take me more than one conversion step if the word mole isn't in the problem. So I know I'm going to have to do more than one here. So I'm going to set it up, my 64.25 liters CO2. Going to diagonal my liters down here, liters CO2, because I want to cancel that, goes in the bottom, and I'm going to go to the mole. I got to make a pit stop at the mole first. So 1 mole of CO2, and we know that that's 22.4 liters. We already know that value. Now I'm going to keep adding on to my track to go from moles to molecules. So now I take my moles of CO2, I put that down here, moles of CO2, and that's going to equal my molecules of CO2. 1 mole, what's the number for any type of particle, which molecules happens to be a particle, so what's that number that I put up here? What number goes with molecules? Atoms, formula units, ions. What value do we always assign to any type of particle? Yes, Avogadro's number. So this is 6.02 times 10 to the 23rd. Now let's look at canceling here. I like to cancel in different colors. It makes it easier. Liters cancel with liters. Moles cancel with moles, of course, so that leaves me with molecules. This is what I want. Now, when we're putting this in the calculator, now that it has more than one step, it's going to be 64.25 times 1 times 6.02 times 10 to the 23rd. That's all in the numerator, and then on the bottom it would be 22.4 times 1. Now you don't have to show this step, I'm just, remember the math, we multiply the top, we multiply the bottom, and then we divide it out. So the ones you really don't need to consider because anything times 1 is itself. However, we need to read back over how to put this in the calculator. So the first thing I type is 6.24, and then I'm going to hit the multiply sign. Then I type in 6.02, okay? What you need to do here is then hit second. If you're using a graphing calculator, you need to use the second button, and mine's blue, it's in the upper left corner. Then you want to use the comma. Now the comma should be, if you're using a TI, right above number 7 on your keypad there. What does that do? That inserts this E, okay? So once you do that, then you just type in 23 for the power. Second comma 23. How it should look in your calculator is 64.25 times 6.02 E 23. That's what it should look like in the TI calculator. This makes sure that when you do the calculation, you're not getting anything out of order, because if you try to use the caret button and raise it to the power that way, if you don't put parentheses around the right things, you sometimes get the wrong power at the end. This ensures that you're going to have the correct power in your answer. So, of course, then I would just divide this by 22.4, and then I end up getting my answer. So I'm going to go ahead and do that. 64.25 times 6.02, 23 divided by 22.4. And yes, I ended up getting an answer that says E in here. So it's 1.72671 something times 10 to the 24th. Now in the calculator, it looks like this. It says E 24. What does that mean? That means 10 to the 24th. I do still need to consider significant figures here, so let me do that. For here, looking at this, 4 significant figures. So I'm going to keep 4 of those digits and look for rounding. So 1, 2, 3, 4. Do I round the 6 up or leave it a 6? Round it up, leave it a 6. Round up, okay, good. So this is 1.727 times 10 to the 24th, and this is going to be molecules of CO2. That would be my final answer. Now, if you do not have a graphing calculator and say you're using your phone instead, look for the button that's like this, where it says EE. That will allow you to assign the power as well. So if you find that, it's usually when you're using your phone or something, the regular calculator, if you turn it to the side, it gives you more functions you can use, and you'll see the EE button there, if that's the type of calculator you're using. And yes, correct. All right, now, a little bit different here. We're looking at formula units and grams. 2 things here, formula units and grams. So I'm starting with my 847 grams of ammonium carbonate. Like so, ammonium carbonate. Now, from grams, where do I need to go? I can't go directly to formula units. I need to make a pit stop at the, what's always in the middle of the mole map? The mole, good. So I'm going to the mole, grams to moles, and then from there I can go to formula units. So this is the first step, this is the second step. This one's going to take 2 steps. Now what number goes with formula units? Because it's just another type of particle. What number goes with that? When you see formula units, you should always use this number. Avogadro's number, 6.02 times 10 to the 23rd. Good. Now I'm ready to set it up. So I take my grams, diagonal them down. NH42CO3, that equals 1 mole. NH42CO3. Yes, it becomes tedious to keep writing the formula, but it is a good thing to practice. You'll need to do it later. So before I continue, I need to do the molar mass. I need the periodic table. So I have nitrogen, And that's going to be, if I round this to 2 decimal places, that's 14.01. I need hydrogen, which is 1.01. I need carbon, which is 12.01. And I need oxygen, which is 16. Now that I've found my values, I can get rid of my periodic table. Okay, how many nitrogens in this compound? 2, so I got to multiply this one by 2. How many hydrogens in this compound? 8, so yes, I have to multiply this by 8. So this is 8.08. Obviously, there's only 1 carbon, and then how many oxygens here? Everybody still awake? Hopefully so. 3, yes, okay, 48. Now, if you add all of this up, you'll end up getting 96.11 grams per mole. So you have to do the side calculation here for the molar mass. Now we have the molar mass, we can insert it and continue on with our T-chart. Next thing is we take our moles from right here and we diagonal them down. Moles, NH4, 2, CO3, 1 mole, and then Avogadro's number, 6.02 times 10 to the 23rd, formula units of NH4 to CO3. Once you set all that up, of course, then we can cancel. Let's go with purple. We'll cancel grams with grams, moles with moles, and then we're left with the formula units, which is what we want. Don't forget, yes, we typed this in, 6.02E23. That's how it should look in your calculator if you're using a TI. Times 6.02 divided by our molar mass. And how many significant figures should we care about? We should care about 3, so we're going to round this one to 5.31 times 10 to the 24. Because in my calculator, this is how it's looking. It goes E24. That means this, and that's formula units NH4 CO3. And we are correct. Now I starred these ones because these are a little bit more challenging. All right, a little bit more challenging because this is asking for ammonium ions. And ammonium is just one part of this compound. Oops, that didn't work. Hold on 1 second. Thought I had green, but green did not engage. Okay, so ammonium here. There's a certain amount of ammonium ions in the compound, NH4+. So we need to care about that. Looking at here, ammonium carbonate, how many ammonium ions? So we're starting with grams. Where do we go directly to from grams always? Grams can take us to the mole. Good. From the mole, I can't go directly to ammonium ions, but I can go to the formula units of this compound here. So I can head over to formula units, and that would be Avogadro's number, of course. Now from the formula unit, if you look at this one formula unit, how many ions are in there? How many ions of ammonium are in this formula unit? 2. If you look here, here's the 2. That tells me there's 2 of them. So I can go from formula units to ions at the end here. This is going to take 3 steps though. So I have to set up my T-chart to have 3 steps. Luckily, we've already calculated the molar mass of this. Remember, it's 96.11, so we don't have to do that again. That's from the previous problem. It's the same molar mass, so we're not going to recalculate that. But I have to still write out the compound, which is a pain. So I'm going to go ahead and do that. I'm going to put my grams of ammonium carbonate down here, and that's going to go to the 1 mole of ammonium carbonate. Now I know the molar mass right here, so I can just go ahead and insert it as my conversion factor. I'm going to keep going. Just like the previous problem, we went from moles NH4 plus, or I mean NH4CO3 to the 6.02 times 10 to the 23rd formula units, NH4CO3. Now this last step is the hardest of the whole thing. 1 formula unit of NH4 Now we said that has 2 ions, 2 NH4 plus ions. So really it's pretty much the previous problem except for this added last step here, breaking it up into its ions. Now all we have to do is multiply and divide and cancel. I'm going to go ahead and cancel everything. So grams cancel with grams, moles cancel with moles, formula units cancel with formula units, and now we're left with our ions. So we go ahead, multiply this on the top. Don't forget to use your exponent key, which is the second comma. And then, of course, divide on the bottom by the 96.11. So we end up here, this has 4 sig figs, so I'm going to go with 4 in my answer. I'm getting 1.938 times 10 to the 24 ammonia ions as my final answer. Very good. Just add on that extra step to go between formula units and ions. There's one other little added trick one I'm going to show you here that's also starred because it's more challenging here at this end. How many total ions are there in 45 grams of gold 3 chromate? That's gold 3 chromate, by the way. Okay, so we have grams. Obviously, we're going to go to moles first. Now, we can't get to ions, like I said, till we go to formula units. You have to do formula units first because that's the entire compound, and then at the end, we can split up the ionic compound into its ions. So this one's also going to take 3 steps. 1, 2, 3. The difference is at the ions at the last step. So it's really only different until we get to the end. So if I do 45 right here, 45 grams AU2 CrO4 3. I'm going to diagonal down the grams here and write that there to go to the mole. Go to the mole first. Always the mole. Then you can go between other things. But I have to look up the molar mass of this, and that's going to take a moment because there's lots of elements in there. Oh, did I forget to put the periodic table on here? I guess I did. So let's go ahead and look up these on the periodic table. I forgot to add it to this slide, but I have my hand one here, so I will look them up for us. AU happens to be 196.97. Chromium, if you remember from the previous problem, was 52. And then there is oxygen in here, which is 16. So we know that one pretty well, that we know that one's 16. Start to memorize a few as you use them more often. Now, how many golds are in our formula here? How many golds? Times 2. So we got to multiply that one by 2. Chromium. How many chromiums are in this formula? 3. Good. And then oxygens. How many oxygens are in this formula? 12. Good. Okay, so we have a lot to multiply here to get this molar mass. This is quite a massive molar mass. 196.97 times 2, 393.94, 52 times 3, this is 156, and then 16 times 12 is 92. So then we add all this up, and we end up getting our molar mass, which looks like it's in the 700s, right? 741.94 grams per mole. Wow, very large mass. Very good. Okay, so we're there. Now we go, got that molar mass. We're going to take the moles, diagonal them down. AU2CrO43, and we're going to formula units. What is the number for formula units again? It's a type of particle. How many of these particles? We got to start remembering, what is formulas units number always? What is molecules, atoms, ions, formula units? What are we doing there? Formula units going to be what? 6.02 times 10 to the 23rd. And this would be formula units of AU2CrO43. Wow, fun compound to write out. One last step. Now, one formula unit of this compound, AU2CrO43. How many ions in here? Now we know it's Au3+, we know CrO4 is -2. You could look up the ions and figure out the charge on the gold if you're, looking at the formula and trying to figure out the name. How many of each do we have here? We have 2 of the gold, 3 of the chromates. So how many total ions do we have in that formula unit? 3, 2, right? We have 2 of these, 3 of those. To make it add up to 0, right? So how many total ions in that formula unit? 5. So this is what we put here, 5 total ions. Now all you have to do is multiply 45 times 6.02 to the 23rd times 5 divided by the molar mass, which is 741.94. And we end up with our total ions, which is 1 point, and there's only 2 sig figs here, 2. So I'm only going to round it to 2. So this is 1.8 times 10 to the 23rd ions of AU2CrO43. Total ions, I guess, I could put in that particular compound.